Look around you, in the walls of our homes, beneath the floors of our offices, stretching across the vast landscapes of industrial plants. It is a system of pathways that carries the lifeblood of our modern world: cable trays, electricity, and data. We rarely see it. We almost never think about it. Yet, without this intricate circulatory system, our society would grind to a halt. The lights would go out. The internet would cease to function. The factories that produce our goods would fall silent. The power plants that energize our cities would fall silent. These silent, dutiful structures are the arteries and veins of our technological civilization, ensuring power and information flow reliably and safely to where they are needed most. This story is about one of the most fundamental components of that network. It is an exploration of an unsung hero of engineering: the cable tray. These simple yet ingenious structures are the backbone of modern electrical and data infrastructure. They are not as glamorous as the microchip or as visible as the skyscraper, but they are just as crucial. From the scorching deserts of the Middle East to the frozen plains of Siberia, cable trays provide a robust, organized, and secure method for managing the vast bundles of wires that power our world. This essay will take you on a journey from the past to the present, revealing the critical role these humble metal and composite structures play in our daily lives. We will begin our narrative in the post-war era, a time of unprecedented industrial expansion. It was an age of ambition, where new technologies were rapidly transforming society. In the burgeoning petrochemical plants and sprawling factories of the 1950s, engineers faced a growing problem: how to manage the ever-increasing complexity of electrical wiring safely and efficiently. The old methods were proving inadequate. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkaragmail.com. Costly and dangerous. Out of this necessity, a new solution was born. This is an Archive to Now story, tracing the evolution of the cable tray from its rudimentary beginnings to the sophisticated, intelligent systems that are shaping the future of industry and technology. The journey of the cable tray is a story of quiet innovation. It reflects the broader history of industrial development itself, a constant search for greater safety, higher efficiency. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkaragmail.com and better performance. This essay will pull back the curtain on this essential piece of hardware. We will examine how it was invented, why it became indispensable, and how it continues to adapt to the demands of a world hungry for more power and faster data. By understanding the cable tray, we gain a deeper appreciation for the complex, interconnected systems that support our technological age. It is a story not just of steel and wire, but of human ingenuity and the relentless drive to build a better, more connected world. To understand the importance of the cable tray, we must travel back in time. The year is 1955. The world is rebuilding and expanding at a remarkable pace. A new kind of industrial giant is rising: the petrochemical refinery. These massive complexes, with their bewildering mazes of pipes, towers, vessels, they were the engines of a new consumer age. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkaragmail.com. They turned crude oil into plastics, fuels, chemicals. But this rapid growth created enormous engineering challenges. The sheer scale and complexity required a staggering amount of electrical power and control wiring. Inside these new refineries, a chaotic and dangerous situation was unfolding. Thousands of electrical cables snaked through the facilities. They were needed to power motors, operate valves, connect control panels. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkaragmail.com. The traditional method was running cables through individual metal pipes called conduits. For a small building, this worked okay. In a sprawling refinery, it became a nightmare. Installing thousands of separate conduits was time-consuming and expensive. Electricians had to bend and fit each pipe, pull individual cables through them, secure every connection. It was slow, and it couldn't keep up with construction. Maintenance was a major issue. If one cable failed, finding and replacing it was monumental. Faulty wire might be bundled with dozens inside a sealed pipe. Electricians would have to de-energize a whole section, pull out all the cables, then feed them all back in. That meant extended downtime for a 24/7 facility. Safety was another concern. Heat from many power cables trapped in a sealed pipe created a fire hazard. In that high-stakes environment, a new idea began to take shape. Engineers and contractors experimented with a different approach. Instead of sealed pipes, they proposed an open, trough-like support. The cable tray. Early versions were basic, custom fabricated from angle iron steel bars, resembling a simple ladder. Cables could be laid in quickly without pulling them through pipes, an elegant solution born from necessity. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkarigmail.com. So, what exactly is a cable tray? In its simplest form, a cable tray is a structural system used to securely fasten and support electrical cables and raceways. Think of it as a bridge or a highway system designed specifically for wiring. Instead of letting cables lie on the ground or hang haphazardly, the tray provides a clear, organized, and protected path for them to follow. These systems are typically made from durable, corrosion-resistant materials like steel, aluminum, fiberglass. They're not just simple troughs. They're engineered components, designed to handle specific loads, span distances, and withstand harsh environmental conditions. Forming the skeletal framework of an electrical installation, a cable tray system is a collection of components that fit together. It includes straight sections that form the main pathways. It also includes fittings to change direction or level, elbows for turning corners, T's for creating branches, risers for vertical transitions between floors. This modularity is a major strength. It lets engineers design custom pathways for buildings, for industrial facilities, navigating around obstacles like pipes, support beams, other equipment. The system is supported by hangers or brackets. Hangers and brackets attached to walls, ceilings, or floors. Several distinct types exist. Ladder tray. 2 side rails connected by rungs, like a ladder. Strong design. Excellent air circulation to dissipate heat. Easy to tie down cables. Perforated tray. Ventilated bottom with side rails. More support for smaller cables, with ventilation. Solid bottom tray. Maximum protection for sensitive cables. Less ventilation. Wire mesh trays, also called cable baskets. Lightweight, flexible, easy to cut and shape on site. Ideal for data and communication wiring. The fundamental purpose is to create order out of chaos. In large projects, a data center, a manufacturing plant, there can be hundreds or thousands of cables. Without management, wires become tangled, unsafe, and unmanageable. Cable trays provide a designated route. They ensure power cables are separated from sensitive data cables to prevent interference. They make installation faster, maintenance simpler, and the entire electrical system safer. They are the physical grid organizing power and information, transforming a jumble of wires into a highly organized and efficient network. The shift from individual conduits to open cable tray systems was not just a minor change, it was a paradigm shift in electrical engineering. The reasons for this shift are rooted in 4 key advantages: safety, cost-effectiveness, flexibility, ease of maintenance. These benefits are so significant, they've made cable trays the standard for industrial and large commercial projects worldwide. Understanding why they matter is to understand core principles of modern electrical design, where efficiency and safety are paramount. The adoption of cable trays resolved many critical flaws in older wiring methods, paving the way for larger and more complex installations than ever before. First and foremost, cable trays dramatically improve safety. One of the biggest dangers in high-density wiring is the buildup of heat. When multiple power cables are bundled together inside a sealed conduit, the heat they generate has nowhere to go. This can cause the cable insulation to degrade and eventually fail, creating a risk of short circuits and fire. Ladder and perforated cable trays, with their open designs, allow for natural air convection to cool the cables effectively. This ventilation significantly reduces the risk of overheating. Furthermore, in the event of a fire, cables in an open tray are easier for fire suppression systems to reach, and the system prevents fire from propagating along the inside of a sealed conduit. The economic advantages are undeniable. The total installed cost of a cable tray system is often significantly lower than that of a conduit system for the same number of cables. The material cost per foot for a tray is higher than for a single conduit, but the tray can hold many cables. The real savings, however, come from labor. Installing a cable tray is much faster than bending, fitting, and mounting hundreds of individual conduits. Once the tray is in place, electricians can simply lay the cables in, rather than pulling them through long pipe runs. This reduction in labor time translates directly into major cost savings, allowing projects to be completed faster and on budget. Finally, cable trays offer unparalleled flexibility and ease of maintenance. Industries are not static. They change and grow. With a cable tray system, adding new cables for new machinery is a simple process. You just open a section of the tray, lay in the new cable, and secure it. In a conduit system, adding a new circuit might require installing a completely new pipe from the power source to the equipment. This flexibility is crucial for facilities that need to adapt to new technologies or production demands. Similarly, maintenance and troubleshooting are simplified. A visual inspection can often identify a damaged cable, and replacing it is as simple as lifting it out and laying in a new one, drastically reducing downtime and repair costs. This essay will now move from the why to the how and where. Having established the historical context and the fundamental importance of cable trays, our journey will now dive deeper into the technical, practical, and global aspects of this essential technology. We will dissect the different types of trays, explore their specific applications, and understand the engineering principles that govern their use. From the factory floor to the offshore oil rig, we will see how these systems are designed, installed, and maintained across a wide range of challenging environments. This exploration will provide a comprehensive view of the cable tray's role as a cornerstone of modern infrastructure. Our first stop will be a detailed examination of the various tray types: ladder trays, perforated trays, solid bottom trays, wire mesh trays. We will explore the specific materials used: galvanized steel, aluminum, stainless steel, fiberglass, and learn why one material is chosen over another depending on the environment. We will also focus on the crucial separation between power and data, looking at how instrument trays and communication trays are specially designed to shield sensitive, low-voltage signals from the electromagnetic interference generated by high-voltage power cables, a critical consideration in any modern automated facility. Next, we will navigate the complex world of codes and standards. The design and installation of cable trays are not arbitrary. They are governed by strict regulations to ensure safety and reliability. We will highlight key articles from the National Electrical Code in the United States and touch upon its counterparts, like the Canadian Electrical Code and international IEC standards. This section will demystify the rules regarding cable fill, spacing, grounding, and structural support. We will also look at the engineering calculations behind a successful installation, including how to determine the right tray size and support span based on cable weight and load capacity. Finally, we will embark on a global tour to witness cable trays in action. We will see how engineers in Texas select trays to withstand scorching sun and heat, while their counterparts in Siberia choose materials that remain durable in temperatures of -50 degrees Celsius. We will visit an offshore rig in India where trays must resist saltwater corrosion, and a facility in Nigeria battling extreme humidity. This global perspective will underscore the versatility and durability of cable tray systems. The essay will conclude by looking to the future, exploring the next generation of smart trays with integrated sensors for predictive maintenance, and reflecting on how this century-old innovation continues to evolve, forming the ever-reliable pathways of power for generations to come. The mid-20th century was a period of explosive industrial growth, and nowhere was this more apparent than in the petrochemical sector. As refineries and chemical plants grew larger and more technologically advanced, they demanded ever-increasing amounts of electricity. This power was not just for lighting. It was the lifeblood for thousands of motors, pumps, heaters, and control systems that operated around the clock. The challenge for engineers was immense: how to route and protect the vast networks of cabling required to run these sprawling facilities. The established method, running every cable or small group of cables through individual steel pipes known as electrical conduit, was quickly proving to be a bottleneck. It was a system designed for buildings, not for industrial behemoths that stretched for miles. Imagine the scene at a new plant construction site in the 1950s. Dozens of electricians would be on site, tasked with installing thousands of separate conduit runs. Each pipe had to be measured, cut, threaded, and bent with precision to navigate the complex jungle of process piping, structural steel, and massive vessels. It was a craft that required skill and time, but the sheer volume was overwhelming. Pulling the cables through these long, winding pipes was another slow, arduous task. This process was creating significant delays, pushing project timelines, and driving up labor costs astronomically. The conduit system, once a symbol of robust electrical protection, was becoming a source of immense frustration and inefficiency in this new industrial age. The problems extended deep into the operational life of the plant. Heat, the eternal enemy of electrical wiring, became a critical concern. As power cables carry current, they generate heat. When many of these cables are packed tightly together inside a sealed metal pipe, that heat has no way to dissipate. The ambient temperature inside the conduit could rise to dangerous levels, causing the cable insulation to degrade, become brittle, and eventually fail. This created a persistent risk of short circuits, equipment failure, and, most alarmingly, electrical fires. In an environment filled with flammable materials, a single electrical fault could have catastrophic consequences, making the conduit method a hidden but significant safety liability. This convergence of cost, time, and safety issues created a powerful incentive for innovation. The industry was hitting a wall, constrained by a method that could not scale to meet its ambitions. Engineers and contractors on the front lines recognized that a fundamentally different approach was needed. They required a system that was faster to install, cheaper to procure and manage, and inherently safer by design. The pressure was on to find a solution that could support the next wave of industrial expansion without compromising safety or breaking the bank. The stage was set for a revolutionary idea, born not in a research lab, but in the muddy, chaotic, and demanding environment of the industrial construction site itself. Out of the practical challenges faced in the refineries' factories, a simple yet transformative concept emerged. Instead of enclosing cables completely within pipes, why not support them on an open, structural frame? This question led to the invention of the first cable trays. The earliest iterations were rudimentary, fabricated on-site by welding, angle iron flat steel bars. They looked like a simple ladder laid on its side. The ladder tray was born. It provided a strong, continuous support path for cables. Electricians could lay bundles directly onto the rungs, much faster than pulling them through conduits. Adoption was driven by pragmatism, solving an immediate problem. Installation speed increased dramatically. A team could install hundreds of feet of cable tray versus a few dozen conduit runs. This let electrical work keep pace with construction and cut labor costs. Cables and trays were easily accessible and secured with simple ties. Spaghetti wiring gave way to organized pathways. The method solved dangerous heat buildup. Open rungs allowed air to circulate around cables. Natural convection carried heat away, keeping cables cool and safe. Engineers could use smaller gauge cables or pack more cables into the same space. That improved ampacity, brought more savings and efficiency. The ladder tray became part of the system's thermal management. Entrepreneurs and manufacturers noticed the market. They began to standardize designs into modular systems, straight sections fittings, supports that could be mass-produced. the cable tray shifted from field fix to engineered product. Companies like TJ Cope began marketing full systems. Commercialization made the tech accessible and consistent. That paved the way for adoption beyond petrochemical plants. Section 3. Beyond the refinery. The spread of a simple idea. While the petrochemical industry was the incubator for the cable tray, the compelling advantages of the system meant it would not remain confined there for long. Engineers and project managers from other heavy industries began to take notice. Pulp and paper mills, automotive manufacturing plants, steel foundries. These facilities shared many of the same challenges. They were large, complex, and required extensive electrical networks. They also operated in harsh environments where durability and ease of maintenance were critical. The cable tray system, having proven its worth in the demanding oil and gas sector, was a natural fit for these applications. The transition into general manufacturing was seamless. In an automotive plant, for instance, production lines are frequently reconfigured to build new models. The flexibility of cable trays was a perfect match for this dynamic environment. Adding or rerouting power for a new robotic welder or conveyor system was a straightforward task. Instead of installing entirely new conduit runs, technicians could simply lay new cables into the existing tray infrastructure. This ability to adapt quickly with minimal downtime was a huge competitive advantage. The open nature of the trays also made troubleshooting on a noisy and complex factory floor much simpler, as technicians could visually trace cables from the control panel to the machine. The next logical step in the expansion of cable tray use was into power generation itself. Fossil fuel power plants, hydroelectric power plants. These high-voltage cables are thick, heavy, and generate significant heat. Ladder-style cable trays, with their high strength and excellent ventilation, were the ideal solution for managing these behemoths. They provided the robust structural support needed to handle the immense weight of the cables over long spans, while the open design ensured they remained cool and operated safely. The use of cable trays became standard practice in the construction of new power stations around the world. Even large commercial buildings and infrastructure projects began to adopt the technology, particularly wire mesh and perforated tray types. Airports, data centers. In these applications, the primary driver was often the need to manage thousands of smaller communication and data cables alongside power wiring. The lightweight and easily modifiable nature of wire mesh cable baskets made them perfect for routing the complex web of Ethernet and fiber optic cables. By the 1970s and 1980s, the cable tray had evolved from a niche industrial solution into a versatile and ubiquitous component of almost any large-scale construction project. Section 4. The economics of simplicity. Conduit versus tray. The most powerful argument for the adoption of cable trays has always been economic. While safety and flexibility are crucial, the decision to switch from a century-old method like conduit to a new system often comes down to the bottom line. The cost equation for cable trays versus conduit is not just about the price of materials, it is about the total installed cost, which is dominated by labor. In a direct comparison, a single length of cable tray is more expensive than a single length of conduit. However, that single tray can replace dozens of individual conduit runs, and this is where the economic calculus begins to shift dramatically in the tray's favor. The primary source of savings is the drastic reduction in installation time. Consider a scenario requiring 100 cables to be run over a distance of 300 feet. With conduit, this would require an enormous amount of labor. Electricians would have to install, secure, and connect potentially hundreds of 10-foot sections of pipe. Each connection has to be tightened, and each bend has to be carefully crafted. After the pipe system is built, the even more time-consuming task of pulling each of the 100 cables through the pipes begins. This entire process can take a team of electricians many days or even weeks to complete, accumulating thousands of hours of expensive labor. Now, consider the same scenario with a cable tray system. The crew installs the support hangers and then bolts together 30-foot straight sections of tray. The entire 300-foot pathway can be assembled in a fraction of the time. Once the tray is in place, the 100 cables are simply unreeled and laid directly into the tray. There is no pulling, no fighting with friction, and no risk of damaging the cable jacket during installation. What took weeks with conduit can often be accomplished in days with cable trays. This acceleration of the electrical scope of work has a ripple effect, allowing other trades to follow behind more quickly and shortening the overall project schedule, which itself represents a massive cost saving. The economic benefits continue over the lifetime of the facility. The cost of labor is not just a factor during initial construction. Every time a new piece of equipment is added or an old one is moved, the wiring must be modified. With a conduit system, these changes are often just as labor-intensive as the original installation. A new dedicated pipe must be run. With a cable tray, however, the existing infrastructure can be reused. Adding a new cable is as simple as laying it into the tray, which might only take a few minutes. This reduces future capital expenditure and minimizes costly production downtime, making the facility more agile and cost-effective to operate over decades of use. Section 5. A breath of fresh air. The safety revolution. Beyond the compelling economic case, the transition to cable trays was a profound step forward in electrical safety. The open design of ladder trays, ventilated trays, directly addressed the hidden danger of heat accumulation that plagued conduit systems. In accordance with the laws of physics, electrical resistance in a conductor generates heat. When many current-carrying conductors are grouped together in a confined space, this heat can build up to dangerous levels. The plastic insulation on cables has a maximum temperature rating. If that temperature is exceeded, the insulation can melt or become brittle, leading to short circuits, ground faults, and the potential for fire. Cable trays fundamentally changed this dynamic by introducing passive cooling. The open structure allows ambient air to circulate freely around the cables through natural convection. Hot air rises away from the cables and is replaced by cooler air from below, creating a continuous cooling cycle. This simple mechanism is remarkably effective at dissipating heat, ensuring that the cables operate well within their temperature limits. This not only prevents insulation damage and reduces fire risk, but also improves the overall efficiency of the electrical system, as conductors operate more effectively at cooler temperatures. The result is a more reliable and inherently safer installation. Another significant safety benefit relates to the behavior of cables during a fire. In a traditional conduit installation, a fire that starts at one end of a pipe can propagate through the entire length of the conduit, using the cable insulation as fuel in an enclosed, chimney-like space. This can allow a fire to spread unseen through walls and floors to other parts of a building. In an open cable tray system, this risk is mitigated. Cables are exposed, allowing fire suppression systems like sprinklers to directly target the burning materials. Furthermore, fire retardant coatings on cables and fire stop barriers at wall penetrations make it easier to contain a fire to a single area. The safety improvements also extend to the personnel working on the system. Visually tracing a circuit in a complex industrial setting is far easier when the cable is visible on a tray. This reduces the risk of an electrician accidentally working on the wrong, potentially energized circuit. During maintenance or fault finding, the accessibility of cables in a tray means that workers spend less time in potentially hazardous areas. They can quickly identify and replace a damaged cable without the complex and physically demanding process of pulling multiple cables out of a long conduit. This reduces physical strain and minimizes the time that electrical systems need to be de-energized, creating a safer working environment for maintenance staff. Industrial and commercial facilities are not static monuments. They are living, breathing entities. They must evolve to meet new demands, adopt new technologies, and optimize their processes. The inherent flexibility of cable tray systems provides a crucial future-proofing advantage rigid conduit systems simply cannot match. This is the flexibility dividend, an ongoing return on the initial investment over a facility's life. It turns the electrical grid from fixed to dynamic and adaptable. Consider the life cycle of a modern factory. Over a 20-year period, production lines may be overhauled multiple times. New, more efficient machinery replaces the old. Robotic automation is introduced. Control systems are upgraded from analog to digital. Each change requires significant wiring modifications. With a cable tray system, The process is simplified. Main tray highways often have spare capacity planned. Adding a circuit can be as simple as running a new cable from the power panel to the machine and laying it in the existing tray alongside other cables. This agility is essential for staying competitive. In data centers, flexibility is even more critical. The pace of technological change is relentless. Servers are replaced every few years. Network standards evolve. Demand for bandwidth skyrockets. Data centers must scale and reconfigure cabling quickly without disruption. Wire mesh cable trays are the standard. They can be cut and shaped on-site to navigate dense racks. Fiber optic data cables and copper data cables can be added, removed, or rerouted with minimal effort, keeping up with demand for information. Flexibility also means decommissioning old cables. When machinery is retired, power and control cables go redundant. In conduit systems, dead cables are often abandoned because removal is costly. Conduits can become clogged with unused wires, blocking new additions. In cable trays, removing old cables is as easy as cutting ties and lifting them out. This keeps pathways clean, organized, and available for future use, preserves the value of the infrastructure, and prevents decay into a tangled, unmanageable mess. For the maintenance technicians and electricians, the shift from conduit to cable trays was nothing short of a revolution. The daily reality of their job was transformed. The task of troubleshooting an electrical fault changed from a blind, frustrating search into a straightforward process of visual inspection and direct access. In a complex plant, where a single machine failure can halt production and cost thousands of dollars per minute, the ability to find and fix a problem quickly is of paramount importance. Cable trays make this rapid response possible. Imagine a critical motor on a production line stops working. In a facility wired with conduit, the troubleshooting process is difficult. The maintenance electrician must first consult electrical drawings to identify which circuit powers the motor. Then, they must locate both ends of the conduit run, which could be hundreds of feet apart. To test the cable for faults, they would have to de-energize it, disconnect it at both ends, and perform electrical tests. If the cable itself is faulty, the real work begins, pulling the old cable out, which may be stuck, and then pulling a new one in. This entire process is time-consuming and often requires multiple people. Now picture the same scenario in a facility with cable trays. The electrician can visually trace the cable from the motor back towards the power panel. The cable is right there in the open, on the tray. A visual inspection along its length might immediately reveal the problem. Perhaps a section with visible damage from an impact or abrasion. If a test is needed, access points are readily available. If the cable needs to be replaced, the process is simple. Disconnect it, cut the cable ties, lift the old cable out, lay a new one in its place, and reconnect it. What could have been a half-day job with conduit becomes a task that might be completed in under an hour. This ease of access also encourages proactive, preventative maintenance. Because the cables are visible, routine inspections can spot potential problems before they lead to a failure. Technicians can identify cables that are sagging, improperly supported, or showing early signs of wear on their insulation. They can ensure that power and data cables remain properly separated and that there is no buildup of dust or debris in the trays that could impede ventilation. This ability to see the entire system at a glance allows for a more holistic and preventative approach to electrical maintenance, improving overall system reliability and extending the life of the infrastructure. The cable tray doesn't just support cables, it supports the people who maintain them. Section 1. The Rulebook of the Grid. An introduction to electrical codes. The installation of a cable tray system is not an act of improvisation. It is a precise and carefully regulated discipline, governed by comprehensive rulebooks known as electrical codes. These codes are the culmination of over a century of experience, research, and lessons learned. They exist to ensure the safety of people and property. For engineers, these codes are not mere suggestions. They are the law. For installers, these codes are not mere suggestions. They are the law. For inspectors, these codes are not mere suggestions. They are the law. They provide a common, standardized language for electrical safety. Ensuring an installation in one city is as safe as one thousands of miles away. This framework transforms metal parts into a safe, functioning grid. The National Electrical Code in the United States. The Canadian Electrical Code. Standards from the International Electrotechnical Commission. They provide a detailed blueprint for every aspect of installation. They dictate not just what can be installed, but how it must be installed. Types of cables permitted in a tray. Maximum weight the tray must support. Precise methods for ensuring the system is properly grounded. They are dense, technical documents, the bedrock of our electrical infrastructure. The codes move beyond theory to practical, enforceable rules. They address real-world challenges of building and maintaining systems. Minimum bending radius for different cable types. Maximum distance between tray supports to prevent sagging. High-voltage power cables. Low-voltage data cables. Requirements for separating them to prevent electromagnetic interference. Adherence is not optional. It's a legal and ethical obligation. Understanding the regulatory landscape is essential to appreciating cable trays. Tray design, innovations in tray materials, installation techniques. Codes create checks and balances as technology evolves. We'll explore key principles, global application, and engineering calculations. Section 2. The American Standard. Navigating the NEC. Article 392. The definitive guide for cable tray installation in the U.S. is NEC Article 392. It's the primary reference for engineers, electricians, inspectors. It provides a comprehensive set of rules that govern every facet of a cable tray system. It defines what a cable tray is. It outlines permitted uses. Permitted use, service conductors, feeders, branch circuits, communication circuits. This recognition gives authorities the legal basis to approve or reject an installation. Article 392 is like the Constitution of the American cable tray industry. A critical section covers installation requirements for the cables themselves. The code lists permitted cable types. Example: TC-rated cables. TC cables are flame retardant and crush resistant. The code lays out cable fill rules. Fill rules dictate max cross-sectional area per tray width and type. This prevents overheating. Limiting cable density ensures air circulation for heat dissipation. Structural integrity is another major focus. Trays must be installed as a complete system. All fittings, bends, and connections must use components for that tray type. The code specifies securing and support requirements. Trays must handle cable weight without excessive deflection or collapse. The code contains detailed grounding and bonding rules. Every metallic component must be electrically connected to form a continuous path to ground. That prevents the tray from becoming a shock hazard in a fault. Section 3. Beyond Borders. The influence of CEC and IEC standards. While the NEC sets the standard in the United States, electrical safety is a global concern. In Canada, the Canadian Electrical Code serves a similar function to the NEC. Many of the core principles are shared. Proper grounding, cable fill, structural support. The CEC has its own unique requirements and interpretations. For manufacturers and engineering firms operating in both the United States and Canada, understanding the subtle but important differences is essential for compliance and market access. The international landscape is largely shaped by the International Electrotechnical Commission, based in Geneva, Switzerland. The IEC develops and publishes a vast portfolio of standards. The key standard for cable trays is IEC 61537, Cable Management, Cable Tray Systems, and Cable Ladder Systems. Unlike the NEC, which is an installation code, IEC 61537 is primarily a product standard. It defines technical requirements, classifications, testing methods for the trays themselves. It ensures that a cable tray manufactured in Germany meets the same performance criteria as one made in Japan, fostering a global marketplace for these products. It establishes a rigorous testing protocol where a section of tray is loaded to 1.7 times its claimed safe working load without collapsing. This provides a crucial safety factor and gives engineers confidence that the product will perform as specified. This creates a two-tiered system. The IEC standardizes the product, and national codes standardize its installation. This global ecosystem of codes, while complex, has been incredibly successful in promoting electrical safety worldwide. It allows a multinational corporation to apply consistent engineering principles whether they are building a factory in Texas, a mine in Ontario, or a data center in Frankfurt. The harmonization of testing methods and safety principles means that best practices are shared across borders. It ensures that regardless of the local language or jurisdiction, the fundamental goal remains the same: to create a cable management system that is robust, reliable, and, above all, safe for the people who build it, people who operate it, and people who work around it every day. Beyond the legally mandated electrical codes, like the NEC and the CEC, there is another layer of standardization that plays a crucial role in the industry: the standards published by trade associations, most notably the National Electrical Manufacturers Association, or NEMA, in the United States. NEMA's standards are not law, but they are created by the manufacturers themselves to establish a baseline for product performance, construction, and classification. These unwritten rules are so widely adopted that they have become a de facto requirement for doing business. Specifying a NEMA 12A rated tray, for example, is a shorthand that every engineer and supplier in the industry understands. NEMA publishes several key standards related to cable trays, such as NEMA VE1 for metal trays and NEMA FG1 for fiberglass trays. These documents establish standard classes for load capacity and span. For instance, NEMA VE1 defines load span classes. See the load span table. The number 8 refers to load capacity in pounds per foot. The number 12 refers to load capacity in pounds per foot. The number 20 refers to load capacity in pounds per foot. The letter A refers to support span, 8 feet. The letter B refers to support span, 12 feet. The letter C refers to support span, 20 feet. This classification system provides a simple, standardized way for an engineer to specify required tray performance without detailing every aspect of construction. These standards also provide guidance on testing procedures. They provide guidance on finish classifications for corrosion resistance. And they cover other manufacturing details. By adhering to NEMA standards, manufacturers ensure their products are interoperable and can be compared fairly. It creates a level playing field and gives customers confidence that products meet a recognized benchmark of quality and strength. While compliance with NEMA standards is voluntary, most major industrial projects will specify NEMA-compliant trays, making it a commercial necessity. Finally, the most detailed source of information is the manufacturer's own product catalog and engineering data. These documents provide specific load tables. They list part numbers, and they include installation instructions. Manufacturer data gives installers precise details they need, such as the correct torque for splice plate bolts, or the specific part number for a vertical adjustable bend. The combination of mandatory legal codes, voluntary industry standards, and detailed manufacturer data forms a comprehensive pyramid of information that guides a cable tray system from the drawing board to a safe final installation. Cable trays are a truly global technology, but their application is not one size fits all. The choice of tray type, material, and coating reflects local environment, industry, and economics. Texas refinery, scorching heat; Siberia, frozen expanse; offshore rig in the Indian Ocean, salty spray. A global map shows animated lines and tray icons across continents. Embark on a global tour visiting diverse industrial sites: North America and Europe, Asia, Africa. Case study: engineers examining site-specific challenges. Material science put to the test: hot dip galvanized steel, aluminum, stainless steel, fiberglass. Tray types: heavy-duty ladder trays for power, dust-resistant covered trays for sensitive electronics. Engineers adapting designs and installations on site. Structures built to perform reliably for decades in punishing environments. The cable tray is an active participant in the battle against the elements. Nigeria, humid, corrosive coast. French nuclear power plant, clean, controlled environment. Lessons in trade-offs: balancing cost, longevity, and performance. from codes and standards to tangible industrial infrastructure. The humble cable tray, indispensable, silently and reliably powering our planet. Our first stop is the Gulf Coast of Texas, the heart of the American petrochemical industry. Sprawling refineries' chemical plants operate under a relentless sun, summer temperatures regularly soaring above 100 degrees Fahrenheit, 38 degrees Celsius. And in this environment, the primary enemy is heat, both from the ambient air and from the powerful electrical cables themselves. The cable tray systems here are not just supporting wires, they are critical components of a massive thermal management system. The engineering choices made here are all about maximizing ventilation and ensuring long-term durability under constant thermal stress and UV exposure. The dominant choice in these facilities is the heavy-duty, marine-grade aluminum ladder tray. Aluminum is selected for several key reasons. First, its excellent corrosion resistance. Second, its high thermal conductivity helps it act like a heat sink. Most importantly, its lightweight makes installation safer and easier. The use of steel is less common, reserved for areas requiring extreme strength or specific chemical resistance. The ladder tray design is non-negotiable in this high heat environment. Its open structure provides the maximum possible ventilation, allowing cooling breezes to flow freely around the power cables. This is critical for maintaining the ampacity or current carrying capacity of the cables. Engineers must perform detailed calculations that account for the solar loading, the direct heating effect of the sun on the trays and cables. To mitigate this, trays are sometimes installed with ventilated covers. These covers provide a shield from direct sunlight while still allowing hot air to escape through the vents, creating a chimney effect that enhances natural convection and cooling. Durability is paramount. A tray failure in one of these continuously operating plants could lead to a catastrophic shutdown. Therefore, the systems are robustly engineered, using heavy-gauge aluminum and strong, well-spaced supports. The expansion and contraction of the long metal tray runs due to daily temperature swings must also be managed. Special expansion splice plates are installed at regular intervals to allow the tray to grow and shrink without buckling or placing stress on the supports. The Texas refinery is a perfect example of how cable tray engineering is adapted to conquer an environment of extreme heat and solar radiation. Section 7. The Great Wall of Wires, Dust and Scale in China. Our journey now takes us to northeast China, the vast Daking oil field, one of the country's largest and oldest. The environment here presents a different set of challenges. Temperatures can be extreme, but a more persistent problem is the fine, abrasive dust blowing in from the plains, and the industrial grit of older, large-scale facilities. That dust accumulates in trays, trapping heat and moisture. That trapped moisture leads to corrosion, and it causes insulation breakdown. Engineers must balance airflow with protection from particulate contamination. In control centers, the preferred solution is hot-dip galvanized steel trays. In substations, the same solution is common. Trays may have a solid bottom, or a perforated bottom, often fitted with a tight-fitting cover. Hot-dip galvanizing gives robust, long-term corrosion protection at low cost. Covered trough-style trays shield control and communication cables from dust ingress. That protection reduces ventilation, a necessary trade-off for instrument reliability. The scale is staggering, miles upon miles of cable tray. A great wall of wires forming the plant's central nervous system. Logistics favor standardized, mass-produced components. Galvanized steel is the industry workhorse, widely available and cost-effective. The design philosophy, durability and simplicity, built to last decades with minimal maintenance. Ladder-style trays still handle heavy power distribution in the field. Even ladder trays may get peaked covers, or watershed covers. Covers keep dust off the cables. They keep rain off the cables. They prevent snow accumulation in winter. Peaked shapes let snow slide off, avoiding heavy loads. Daking's cable tray solutions are a pragmatic masterclass, balancing cost, scale, and pervasive dust. Section 8. The Jewel of the Sea. Resisting salt on India's offshore rigs. We now travel to the Arabian Sea, off the coast of Mumbai. an offshore oil and gas platform run by ONGC. The cable tray system here faces one of the most corrosive environments on Earth. Constant salt spray, high humidity, intense sun. A galvanized steel tray that lasts decades on shore can rust away in just a few years offshore. The primary engineering challenge: conquer corrosion. Material selection is critical. Stainless steel fiberglass, FRP. Stainless ladder trays for main pipe racks and heavy high-voltage cables. Type 316L stainless steel with molybdenum resists chloride corrosion. High upfront cost, but long-term longevity and fewer replacements. Fiberglass trays for instrumentation and chemically aggressive areas. FRP is immune to saltwater corrosion and non-conductive. Fiberglass is lightweight, easier and safer for crews. Bright yellow fiberglass trays against the blue sea. Every component must resist corrosion. Nuts, bolts, clamps, all Type 316 stainless steel. UV-resistant, marine-grade cable ties securing wires. Holistic engineering approach to survival on a rig. Extreme environments demand advanced materials, protecting vital energy infrastructure. Section 9. The Siberian Challenge. Enduring the deep freeze in Russia. Our global tour now takes a dramatic turn, heading north to the vast frozen oil and gas fields of Siberia, Russia. Here, the challenge is not heat or salt, but a cold so profound it can make steel as brittle as glass. Winter temperatures can plummet to -50 degrees Celsius and remain below freezing for more than half the year. In this environment, the primary engineering concern is material performance at extreme low temperatures. A material that is strong and ductile at room temperature can shatter under impact in the Siberian deep freeze. The reliability of the cable tray system is critical, as maintenance and repair in these conditions are incredibly difficult and dangerous. The material of choice in this brutal climate is often a specially treated, hot-dip galvanized steel. Increasingly, fiberglass, FRP, is also used. Unlike metals, FRP composites do not become brittle in the cold. They maintain their strength and impact resistance even at -50 degrees Celsius. Their lightweight nature is also a significant advantage for construction crews who must work quickly and efficiently in bulky protective clothing. Furthermore, the buildup of ice and snow can add a tremendous amount of weight to the tray system. Engineers must account for this additional load in their span and support calculations, often specifying shorter spans and heavier-duty support structures than in temperate climates. Covers are universally used on outdoor tray runs in Siberia. These covers are not primarily for dust or sun protection, but to prevent the trays from filling up with snow and ice. A peaked or watershed-style cover is essential to shed snow and reduce the static load on the system. The entire installation is a testament to engineering for the worst-case scenario. From material selection to load calculations that include the weight of ice, every decision is made with the deep freeze in mind. The Siberian cable tray is a symbol of resilience, proving that with careful engineering, the pathways of power can be maintained even in the coldest and most inhospitable places on Earth. Section 10. The Tropical Test. Humidity and heat in Nigeria. Leaving the frozen north, arriving in the Niger Delta region, home to one of Africa's largest oil and gas industries, including massive liquefied natural gas, LNG, plants. The environment here is the polar opposite of Siberia, a relentless combination of high heat, often exceeding 35 degrees Celsius, 95 degrees Fahrenheit, and extreme humidity that can approach 100%. This tropical climate creates a perfect storm for corrosion. The constant moisture acts as an electrolyte, accelerating the rusting of unprotected steel, while the heat speeds up all chemical reactions. The challenge for engineers is to specify a cable tray system that can resist this pervasive, corrosive dampness for decades. The go-to material for this environment is aluminum, specifically marine-grade alloys. Aluminum's natural ability to form a protective oxide layer makes it highly resistant to atmospheric corrosion. It provides a long, maintenance-free life without the need for painting or recoating, which is a significant advantage in a remote and challenging operational environment. Hot-dip galvanized steel is also used, but aluminum is often preferred. Aluminum resists the uniform corrosion that thrives in warm, wet climates, and it's lighter weight, which simplifies installation. Ventilation is another top priority. In a high-humidity environment, trapping air can lead to condensation where moisture collects inside the tray. This is why open ladder-type trays are heavily favored over trough designs, or solid-bottom designs. The open structure allows constant airflow, which helps to dry out any moisture and dissipate heat from the cables. Even with ladder trays, installations may include drain holes at low points to ensure collected rainwater can escape quickly, preventing pools of stagnant water and localized corrosion hotspots. The Nigerian LNG plant serves as a powerful case study in combating the subtle but destructive power of humidity. It shows that the engineering battle is not always against extreme forces like salt spray or deep freezes, but sometimes against the quiet, persistent, and pervasive influence of a tropical atmosphere. Section 11. The European Theater, Precision in UK and French Nuclear Sectors. Our final stop. The highly regulated, safety-critical nuclear industry in the UK and France. Engineering challenges here are about precision, documentation, and safety. A cable tray failure in a nuclear plant is unthinkable. It could compromise critical safety systems. Therefore, every component, every weld, every bolt faces unparalleled scrutiny and quality control. The driver is not cost or convenience, but verifiable safety and absolute reliability. Conservative, proven material, and design choices. Hot dip galvanized steel is common. Reason: strength. Reason: fire resistance. Reason: long, reliable track record. In reactor containment, stainless steel is often mandated. For superior strength. For corrosion resistance, so it will perform even in the most severe accident scenarios. Trays are heavy-duty, specified to withstand seismic events and other physical hazards. The system is intentionally over-engineered, nuclear-grade quality assurance and documentation. Every piece, from a straight section to a single bolt, must be fully traceable to the original material batch. Manufacturers supply material test reports and certificates of conformity. Installation is tightly controlled. Every weld inspected, every support location verified against approved drawings. An unbroken chain of accountability from steel mill to final installation. Separation of redundant safety systems is paramount. To prevent one event, like a fire, disabling both primary and backup, cables run in completely separate, physically distant tray systems. Train A train, B other color-coded trains. They are color-coded and run along entirely different routes. Physical and electrical separation, a hallmark of nuclear design. The European nuclear sector, cable tray engineering is not just a pathway for power, but a fully documented, verified, and an essential component of the plant's safety case. Section 12. Engineering for extremes. A battle against the elements. Cable trays are not installed in a vacuum. They live in the real world, under constant assault from nature. Engineers must be strategists in that battle. The forces are immense, crushing weight of snow and ice, corrosive salt and chemicals, thermal expansion and contraction, ultraviolet radiation damage, brute wind forces, seismic shaking. Successful installations anticipate and counter these through design and materials. First line of defense: material. Galvanized steel, aluminum, stainless steel, fiberglass. Material alone isn't enough. Coatings add another armor layer. Pre-galvanized for dry indoor use. Hot dip galvanized for outdoors. Epoxy coatings for corrosive atmospheres. PVC coatings for chemical exposure. These can be factory applied over galvanized steel. Beyond corrosion, physical loads must be managed. Heavy snowfall, Siberia. Heavy snowfall, Canada. Specify higher load ratings and more supports to prevent sag. Earthquakes, California. Earthquakes, Japan. Use sway bracing and flexible couplings so systems move with the building. That keeps power and controls operational. Wind load, exposed pipe racks. Wind load, roofs of buildings. A wide covered tray can act like a sail, catching the wind and loading supports. Engineers use aerodynamic data and wind tunnel testing to design resisting supports. This holistic approach secures long-term grid reliability. It's a testament to engineering winning the battle against the elements. Section 13. The science of support. Understanding load and span. At its core, a cable tray is a structural beam. Its primary function is to carry a load, the weight of the cables, the span between supports, the relationship between load, span, and the strength of the tray is the most fundamental calculation in cable tray engineering. Getting this wrong can have disastrous consequences, leading to a sagging system that damages cables or a catastrophic collapse that endangers lives and halts operations. Understanding the science of support is not an academic exercise. It is a prerequisite for a safe and successful installation. The first step is to calculate the total load. This is determined by adding up the weight of all the cables that will be placed in the tray. Manufacturers provide data on the weight per foot or per meter. An engineer will create a cable schedule, a detailed list of every cable in a given run, and use it to calculate the total anticipated weight per unit length. To this, they must add a safety factor, typically 25% or more, to account for future additions. That gives the total design load for the tray. The next critical variable is the span. This is the distance between the support hangers. A longer span is generally desirable. It reduces the number of supports that need to be installed, saving time and money. However, a longer span places much greater stress on the cable tray. The bending force on a beam increases with the square of the span. Doubling the span from 10 feet to 20 feet does not double the stress. It quadruples it. Therefore, longer spans require significantly stronger and often more expensive cable trays. Manufacturers provide detailed load tables for each of their products. These tables clearly state the maximum allowable load for a given tray at a specific support span. For example, an 18-inch wide aluminum ladder tray can support 50 pounds per foot on a 20-foot span, but could support 100 pounds per foot if the span is reduced to 15 feet. The engineer's job is to select a tray and a support span that can safely handle the calculated design load with a built-in safety margin. This careful, data-driven process ensures the structural integrity of the entire cable management system. Section 14. The engineer's calculation. A practical example. Let's translate the science of support into a practical, real-world calculation. Imagine an engineer is designing a power cable run for a new pump station. The plan calls for a main tray run of 100 feet. The cable schedule shows the total weight is 40 pounds per linear foot. The engineer adds a 25% safety factor for future capacity, bringing the design load to 50 pounds per foot. 40 pounds per linear foot times 1.25 equals 50 pounds per foot. Cable load plus safety factor seeks design load. Snow and ice loads are not a concern for this indoor temperate facility. The engineer's goal: select the most economical tray system that can safely support this load. Structural drawings show strong steel beams available for support every 20 feet. A 20-foot support span would be ideal. It would require only 5 support hangers over the 100-foot run. What tray can handle 50 pounds per foot on a 20-foot span? The engineer turns to manufacturers' catalogs. NEMA load span classification tables. They find a manufacturer's catalog for a standard aluminum ladder tray. Looking at the load table, they search for a tray that meets or exceeds requirements. They find a heavy-duty ladder tray with a NEMA 20C rating. The 20 indicates the class minimum is 20 pounds per foot, but the detailed table shows this tray is actually rated to carry 75 pounds per foot on a 20-foot span. This safely exceeds the required 50 pounds per foot, providing extra margin. The engineer can now confidently specify this tray for the project. This example illustrates the methodical process. Define requirements, calculate loads, consult data, make an informed selection. The engineer documents this calculation as part of the project's engineering package. This ensures the decision can be reviewed by the project manager, client, and electrical inspector. This disciplined approach ensures the system is purposefully engineered for safety and longevity. Section 15. The blueprint for success. Diagrams, drawings, and details. The final output of the engineering process is not the tray itself, but the blueprint that directs its installation. This comes in the form of a detailed set of engineering drawings and specifications. These documents are the definitive guide for the construction team. They translate the engineer's calculations and design intent into a clear visual language that electricians and installers can follow on the job site. A well-designed set of drawings is the single most important factor in ensuring a smooth, efficient, and correct installation. It is the roadmap that prevents confusion, costly mistakes, and delays. These drawings, typically created using computer-aided design software, show the precise routing of the cable tray system throughout the facility. A plan view shows the horizontal layout, much like a roadmap, detailing every straight section, elbow and T. Elevation drawings show the vertical changes, indicating where trays rise or drop to navigate around other equipment. Crucially, these drawings specify the exact location of every support hanger and tie it to the building's structural grid. This removes all guesswork for the installation crew, ensuring the supports are placed exactly where the engineer intended to meet the required span rating. The drawings are filled with a wealth of detail. Each tray run is labeled with a unique identifier and includes notes specifying the tray type, material, width, and depth. Details are provided for non-standard connections or for areas where the tray must interface with other equipment. The drawings will also specify the grounding requirements, showing the location and size of the bonding jumpers used to connect tray sections and the main grounding conductor that connects the entire system to the building's earth grid. Every aspect of the installation is laid out with precision. Accompanying the drawings is a written specification document. This document provides further detail that cannot fit on the drawings, such as the exact part numbers to be used, the required quality standards for materials, and the installation procedures that must be followed. It might specify the exact type of bolts to be used for splice plates, or the minimum required thickness for a hot dip galvanized coating. Together, the drawings and specifications form a complete legal and technical package. They are the contract that defines success. The final word that ensures the finished installation is a perfect reflection of the safe and robust system conceived by the engineer. Our exploration has taken us deep inside the grid, revealing the hidden world of the cable tray. We began in the past, witnessing its birth in the 1950s petrochemical boom. It emerged not as a complex invention, but as a simple, practical solution cost-safety efficiency posed by older conduit systems. This humble ladder of steel provided a faster, safer, and more flexible way to manage the ever-growing web of electrical wiring. Its core advantages were so compelling that it quickly spread from the refinery factories' power plants to nearly every large-scale construction project across the globe, becoming the unseen backbone of our electrified world. We then delved into the anatomy of this technology, dissecting the various types that form the engineer's toolkit. We examined the heavy-duty ladder tray, the workhorse of power distribution, prized for its strength and ventilation. We explored the versatile perforated tray, which balances support and airflow, and the protective solid bottom tray, used for sensitive instrumentation. We also saw the rise of the modern wire mesh basket, whose flexibility has made it the standard for data centers and commercial buildings. This diversity shows how a single concept has been adapted into a sophisticated family of products, each tailored to a specific need, from carrying massive high-voltage cables to cradling delicate fiber optic strands. Our journey then expanded to a global scale, navigating the complex web of codes and standards like the NEC, CEC, and IEC that ensure these systems are installed safely and reliably everywhere. We saw how engineering decisions are shaped by extreme environments, from the intense heat of a Texas summer and the corrosive salt spray of the Indian Ocean to the deep freeze of Siberia and the humid tropics of Nigeria. This world tour demonstrated that the cable tray is not a static object, but a dynamic system, meticulously specified and adapted with different materials. Steel, aluminum, fiberglass, to conquer the unique challenges posed by climate and industry, proving its resilience time and again. Finally, we grounded our understanding in the firm reality of engineering principles. We uncovered the science of support, balancing the critical relationship between cable load span distance and tray strength. We walked through the methodical calculations and saw how they translate into detailed blueprints that guide a safe and successful installation. This entire journey, from its pragmatic origins to its highly engineered present, reveals the story of a technology that is profoundly simple in concept, yet sophisticated in execution. The cable tray's success lies in its ability to bring order, safety, and efficiency to the chaotic and powerful world of electricity, a role it has fulfilled silently for over 70 years. Closing montage. 1950s refinery, modern data center, offshore rig, futuristic plant. As we look toward the horizon, the next evolution of the cable tray is already taking shape. The future is not just about stronger materials or new shapes, it is about intelligence. The next generation of cable trays will be active participants in the digital ecosystem of a facility, transforming from passive support structures into intelligent data-gathering assets. This is the dawn of the smart tray, integrated with sensors and connected to the industrial Internet of Things, the IIoT. These smart trays will provide real-time information about the health and status of the electrical arteries and the data arteries they carry, enabling predictive maintenance and enhanced operational awareness. Imagine a cable tray with tiny embedded sensors. Fiber optic temperature sensors running the length of the tray provide a continuous thermal profile. Operators could detect a potential hotspot, a sign of a failing connection, or an overloaded circuit long before catastrophic failure. Monitoring trends over time lets the system learn normal conditions and automatically flag deviations, sending alerts to maintenance. This shifts from reactive maintenance or scheduled maintenance to a predictive model, fixing problems before they happen. Beyond temperature vibration sensors, weight sensors, security, tamper sensors. Vibration sensors detect unusual shaking that could abrade jackets over time. Weight sensors in hangars monitor tray load, flagging overload conditions if too many new cables are added without proper engineering review. In secure facilities, specialized sensors detect unauthorized cover openings, alerting on potential tampering. The tray no longer just supports the network, it actively monitors and protects it. Data from the smart tray feeds into central control software and maintenance platforms. Managers view a digital dashboard showing health of the cable infrastructure at a glance. Alerts pinpoint exact locations on a three-dimensional model of the facility, guiding crews precisely where to go. This integration of infrastructure and analytics is a profound shift. The humble cable tray becomes a vital data node in the smart factory, and the smart building adding a layer of intelligence to the unseen grid. The future of maintaining cable tray systems will also be transformed by the rise of robotics and autonomous systems, particularly unmanned aerial vehicles, or drones. In vast industrial facilities like refineries or power plants, cable trays are often installed at great heights, in cramped spaces, or in hazardous areas. Inspecting these trays traditionally requires workers to use scissor lifts, scaffolding, or rope access techniques, which can be time-consuming, expensive, and carry inherent safety risks. Drones offer a revolutionary alternative, providing a safe and incredibly efficient way to get a detailed, view from above without ever leaving the ground. A drone equipped with a high-resolution camera can fly along the route of a cable tray run, capturing detailed visual information. The operator, sitting safely in a control room, can zoom in to inspect for signs of corrosion, physical damage, or improper cable installation. This allows for rapid inspection of miles of cable tray in a fraction of the time it would take a human crew. The process is not only faster, but also far safer, as it eliminates the need for personnel to work at height or in potentially dangerous environments. Routine inspections that might have been done annually could now be performed quarterly or even monthly, leading to earlier detection of potential issues. The capabilities of these inspection drones go far beyond a simple visual camera. They can be equipped with a suite of advanced sensors to gather a much richer set of data. A thermal imaging camera, for example, can instantly spot hotspots on cables or connections that are invisible to the naked eye, identifying potential failures before they occur. Drones could also carry laser scanning, LiDAR, other sensors to create a highly accurate three-dimensional point cloud of the installation. This data can be used to check for tray sagging, or to verify that the AS-built installation matches the original engineering drawings, a process that is incredibly difficult to do manually. In the near future, this process will become fully autonomous. An inspection drone could be programmed to fly a predefined route every week, automatically capturing and analyzing data. The system's software would compare the new data with previous scans, using artificial intelligence to automatically flag any changes or anomalies, such as a new spot of corrosion, a loose connection, or a sagging section of tray. This autonomous, data-driven approach to inspection will revolutionize plant maintenance, making it more proactive, more efficient, and dramatically safer for the human workforce who keep our industrial world running. The planning and engineering of cable tray systems are undergoing a profound digital transformation through the adoption of Building Information Modeling, or BIM. BIM is more than just 3D CAD. It's a process of creating and managing a digital twin of a facility. This digital twin is an intelligent 3D model that contains the geometry of every component and a rich database of information about each part. For a cable tray, the model knows its type, material, size, manufacturer, load capacity, and even its maintenance schedule. This integration of cable trays into the BIM ecosystem is revolutionizing how projects are designed, built, and managed. During the design phase, BIM enables unprecedented coordination. Engineers from different disciplines work on the same integrated model: electrical, mechanical, structural. The electrical designer can route the cable tray system in 3 dimensions. BIM software will automatically detect clashes where the tray might hit a pipe, an HVAC duct, or a structural beam. Clash detection lets teams identify and resolve problems in the model before construction begins, preventing costly rework on site. The model ensures a perfect, conflict-free fit. The digital twin also streamlines construction. The BIM model can automatically generate precise material lists, ensuring correct quantities of trays, fittings, supports are ordered. The model can link to fabrication machinery to pre-cut sections off-site and to pre-assemble sections off-site, improving quality and speeding installation. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com. On-site, installers can use tablets or augmented reality glasses to overlay the digital model on the real world, showing exactly where each component should be installed. This removes ambiguity and ensures installation matches the engineered design. The digital twin's value extends through the building's lifecycle. When it's time for maintenance or a renovation, facility managers consult the BIM model to see the exact routing of the cable trays and the cables within them. They use the model to plan new cable runs, check for spare capacity, and understand how changes will impact other building systems. The cable tray becomes a permanent, intelligent element in the building's digital DNA, providing lifetime value from initial design to eventual decommissioning. While the fundamental designs of cable trays have proven remarkably durable, the science behind the materials they are made from is in constant evolution. The future will see new composites and advanced coatings that push the boundaries of what trays can withstand. For technical video generation contact, I text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com. These innovations aim to create systems that are lighter, stronger, more corrosion-resistant, and more environmentally sustainable than ever before. The quest for the perfect material is driving a new wave of R&D to enhance performance and extend service life. In composites, we're moving beyond traditional fiberglass, FRP. Researchers are developing pultruded thermoset composites and pultruded thermoplastic composites. They are incorporating advanced fibers, carbon and aramid, Kevlar. They also improve fire performance with self-extinguishing resins that produce very low smoke and toxicity. That's critical for tunnels, transit systems, and other confined industrial spaces. Another area is self-healing coatings for metal trays. Imagine a galvanized or painted steel tray scratched during installation, exposing bare metal. New coatings contain microscopic capsules filled with a healing agent. When a scratch ruptures those capsules, the agent is released and polymerizes on contact with air, healing the scratch. This could dramatically extend service life by repairing the small nicks that start rust. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com. Sustainability is a major driver of material innovation. Manufacturers are using recycled steel, recycled aluminum, and researching bio-based resins from renewable plant sources. These green materials aim for the same performance while reducing life cycle environmental impact. The cable tray of the future may be stronger, more resilient, and a more responsible choice for tomorrow's infrastructure. The story of the cable tray is a compelling narrative of quiet, essential innovation. It began as a simple ladder of steel, forged by practical necessity. It evolved into the global standard for organizing and protecting the arteries of our technological world. Now it stands on the threshold of a smart, digital future. Its success is proof of a good idea. Improving safety, reducing cost, providing flexibility for a world in constant change. The cable tray is more than hardware. It's unseen engineering that makes modern life possible. Its core purpose will remain: provide a safe, reliable pathway for power and for data. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com. But the nature of those pathways is changing. Smart sensors, robotic inspection, deep embedding in BM models will turn the tray from passive support into an active, intelligent infrastructure. These systems will carry industry lifeblood and monitor its pulse, giving insight into network health and resilience. Advances in materials, self-healing coatings, advanced composites, will let trays survive extreme environments and last generations. Sustainability will drive lighter environmental footprints. The cable tray's story is far from over. It's a story of continuous adaptation and our drive to build bigger, smarter, more efficient systems. It will evolve silently to meet a future hungrier for electricity and information. Contact or text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com. From 1950s refineries to 21st century smart cities, the cable tray has been the constant backbone, a physical manifestation of the grid and human ingenuity. As our future is powered by data centers, renewable energy, global connectivity, we will rely on these pathways more than ever. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com. They will remain unseen, unsung, essential arteries of progress, quietly carrying the power and data that will shape the world for generations, forever forming the enduring pathways of power. For technical video generation contact, text Rajan at +1 587 577 9125 or email at rajanspendharkar@gmail.com.